Hi everyone, I'm Professor McBain and welcome back to Chem 100. This will be the first video in a series on nuclear reactions and how they are utilized across the world for various purposes. And in this video we're just going to really be getting an introduction to the idea of nuclear reactions, the fact that they generate massive amounts of energy, and the fact that we often need to focus in on one particular isotope of a radioactive element in order for those energy yielding processes to be the most efficient. Find out more. All right, let's start in with Lecture 4 on nuclear power and nuclear weapons. This lecture is going to be divided into 3 parts. First, we're going to figure out what chemical reactions are versus nuclear reactions and how we obtain radioactive chemicals in the first place. Then we'll actually talk about nuclear power, and then we'll talk about nuclear weapons. Now, throughout this series, you might hear my little assistant, Freddie, making some noises, so I hope that that's not terribly distracting for you. We're all going to have a good time. All right, so first, let's talk about chemical reactions versus nuclear reactions. We've learned so far that in a chemical reaction, atoms in compounds or molecules can be rearranged to form other molecules, but the atoms themselves remain unchanged. So for example, when octane is combusted in the presence of oxygen in your fuel tank, actually, then all of the carbons and hydrogens and oxygens rearrange themselves so that at the end of this process, and with the help of a catalytic converter, you get carbon dioxide and water as your products. Now in nuclear reactions though, the nature of the atoms themselves changes. The protons, neutrons, and electrons that you have present remain unchanged, but the protons and neutrons rearrange themselves to make new identities of elements. So for example, when uranium-235 undergoes fission, you just start off with a uranium-235 nucleus and a neutron, but then the neutron bombards that uranium-235 nucleus, and then you end up with a barium nucleus, a krypton nucleus, and then 3 more neutrons at the end. Now, what we'll talk about in our activity workshop is the fact that the number of protons and neutrons remains unchanged, like I said. And so that's how you end up being able to balance nuclear reactions. Okay. But again, we'll talk more about this on Wednesday's activity. Why are we even interested in nuclear processes as opposed to chemical processes in the first place? Let's take a look at the breakdown. As you can see here towards the top, let me get my laser pointer, TNT and octane can produce different amounts of energy per gram of fuel that you've got. We'll learn more about this unit of energy called the kilojoule towards week 11 when we talk about energy for reals. But for now, just think about this, that it's a lot like thinking of how many miles per gallon you can get from a fuel, all right? But this is more like how much energy per gram of fuel. Remember that the singular G means gram, not gallon, okay? So TNT can give you 5 kilojoules of energy per gram of TNT. Octane gives you more energy per gram, but if you cause 1 gram of uranium to undergo fission, that will give you 71 million kilojoules of energy. And then furthermore, if you can get some hydrogen nuclei to undergo fusion with each other, then that can give you 600 million kilojoules per gram of fuel. That's a lot of kilojoules. And, well, there are vehicles that use uranium for propulsion. Let's see, what should be here is the picture of a submarine. Nuclear submarines have been in use since the 1950s. But vehicles tend to not use fusion for propulsion because there's an issue. You need a temperature of 40 million degrees Celsius for that reaction to occur. So it's not practical for a vehicle to have that sort of temperature ongoing for a long amount of time. So you'll see fusion in nuclear weapons, and we'll talk about that in a little while, but you tend not to see fusion for propulsion in vehicles. Okay. There's my submarine. Here we go. So uranium is found in nature as two major isotopes. One is uranium-238 and the other is uranium-235. 238 is very abundant, but it's not readily fissionable, so it's not going to undergo that fission process on its own. Whereas 235 will undergo fission, but it's not very abundant, so that's a problem. So in order to make the fission reaction efficient so that you can get a lot of electricity out, we need to enrich the uranium-235. So how do we get uranium? First we have to get it out of the earth, all right, so you have to mine it. And uranium ore contains only about 0.3% of triuranium heptaoxide. Okay, so first you have to crush that ore and separate it from other oxide compounds that are found in the earth. Okay? Then once you've got a sample that consists mostly of triuranium heptaoxide, then you need to convert it to uranium hexafluoride, which we call hex. That process actually involves 1, 2, 3, 4, 5, 6 different chemical reactions, all of which involve the use of dangerous acids as well as solvents, organic solvents. And so all of those processes involve use of some pretty nasty chemicals. Okay? So once you've converted that triuranium heptaoxide into uranium hexafluoride, then you can enrich it. Okay, so uranium hexafluoride exists as a gas, okay, but it's going to consist of some uranium-238 hexafluoride and then uranium-235 hexafluoride. Now, uranium-238 is actually heavier than uranium-235. Makes sense, right? So what you do is you pass your sample of uranium hexafluoride, which contains both of those isotopes, over basically it's a filter, all right? You pass it over many, many times, and the heavier stuff that does not undergo fission will actually fall down through this filter, whereas the lighter stuff that you want to keep will stay on top. So the more and more and more and more that you pass the same sample over these filters, the heavier stuff goes away and then the lighter stuff remains. Okay, so that's how you go through that enrichment process. Okay. So again, everything starts off with only 0.7% uranium-235 hexafluoride. And then eventually you can get low enriched uranium at a rate of 2 to 5%. And then this is acceptable for power plants. You need to undergo enrichment a few more passes in order to get 12 to 19% uranium-235, which is appropriate for research reactors. Now, if you need weapons-grade uranium, then you got to do that process even more so that you've got 85% uranium-235. Let's go back a little bit. So once you've got the amount of uranium-235 that you need for your processes, then it can go to, it can be converted back into uranium oxide, and it will be melted down into fuel rods, and then it'll go to those power reactors, and the energy that is released when that uranium undergoes fission, of course, goes to make electricity, but then the spent fuel, basically it goes to a specialized landfill where the uranium still undergoes fission, but in such a way that it doesn't harm anybody else in the process. So why do we even care about enrichment plants? Well, these days we care about it a lot because our last enrichment plant that we had on United States soil was actually shut down in the year 2013 because even though it was a good thing to have our own enrichment plant so that we can produce our own uranium fuel rods to generate, American electricity, the process was yielding a lot of contamination, which if you're contaminating the surrounding environment with radioactive isotopes, that's a big problem for environmental health, but also human health. Okay, so Paducah's gaseous diffusion plant was contaminating 1.5 to 4 million cubic yards of soil. All right, so all of the soil was contaminated with metal and debris. Okay, so the contaminants were specifically that radioactive uranium, also byproducts of fission, which are also radioactive. But then also the solvents that are used right here in the solvent extraction step of the enrichment process, those solvents are also hazardous chemicals for different reasons. Okay, so those solvents included biphenyls, trichloroethylene, and so on. And so those liquids were being dumped in the creeks nearby. It's not a good thing. Yeah. So the gaseous diffusion plant was shut down in 2013 so that, well, a cleanup could occur. And the cleanup is estimated to be completed by 2040. So that's all well and good, but now the United States needs to obtain its enriched uranium from other countries that are still willing to undergo gaseous diffusion on their own soil, right? So that has its own political issues depending on how you feel about our international relations with countries that we obtain our uranium from. Okay, we're going to take a quick break because my little buddy here is not doing so well.